We open a new chapter dedicating our discussion to image separation and in painting using the SparseLand model. Let's start by presenting the core idea called morphological component analysis. What do we mean by signal separation? Assume that there is a family of signals denoted as X and another different family of signals denoted as Z. Now suppose that we take an instance of each and combine the two linearly, getting to the signal S. It is our assumption that every S we see can be posed as such a mixture, and our goal is to decompose it back to its building ingredients. This is the essence of the separation problem. For example, imagine that the first family of signals are music, while the second corresponds to human voice. Given a song that merges the two, we would like to separate them somehow. Let's bring in the SparseLand model. Considering the signal family X, we assume that there is a dictionary dx that can represent each signal in this set sparsely. So given a signal xk, there is a sparse vector alpha k to represent it. So far, things are rather conventional. Now comes the twist in our story. When using the very same dictionary dx to represent the signal zk from the second family, we would like to demand that sparse representations are impossible. This means that when trying to solve the p0 epsilon problem in this case, the sparsest representation will not be sufficiently sparse. This way, dx has a discrimination power to it. It loves the x's and it hates the z's. Now let's complete the story by assuming that we also have a dictionary dz that behaves in exactly the opposite way, sparsifying the z's while not being able to represent effectively the x's. How do we get dx and dz? Clearly, their content is critical for the success of the separation that is about to come. Observe that these dictionaries carry in them more than just the representation capability for a set of signals as described so far. They should have the ability to distinguish between two sources. In trying to choose these dictionaries, we could either use educated guesses, as we will do shortly, picking well-known transforms, or learn them in a way that optimizes the separation performance. Surprisingly, very few works exist which took the second option, perhaps due to its complexity. Given dx and dz, how should we separate? This is the answer. We should seek the vectors alpha and beta such that dx times alpha plus dz times beta lead to our signal while forcing alpha and beta to be as sparse as they can be. If this is how our approximation looks like, then a sparse alpha will create the x portion, and a sparse beta will generate the z portion in this separation. Theoretically, we know that if alpha and beta are sufficiently sparse, then the above decomposition is unique and will be found by pursuit methods. This is the problem we have just defined. Let's make it a bit more practical by changing the exact equality into an epsilon proximity. This is the morphological component analysis, the MCA, as proposed in 2004 by Stark, Donoho, and myself. What is it looking like? It is a special case of the p0 epsilon problem for which we know so much already.